on 2,612, Birmingham on 2,476 and Manchester on 2,084. The former Prime Minister Gordon Brown and Scottish First Minister John Swinney were among those who gathered at a memorial service on Saturday the 30th of November in Edinburgh for Alex Salmond after his sudden death in October at the age of 69. Kenny McCaskill, a long-time friend of Alex Salmond who served as Justice Secretary and helped him run the Alba Party, paid tribute to him, saying he was a giant of a man who was an inspiration and a political genius. The UK is set to experience more snow this week as temperatures are set to drop to as low as -8 degrees Celsius. There will be widespread frost across the UK and sleet and snow is forecast in Scotland and the northeast of England as cold Arctic air blasts in. And now for African news. 56 people were killed and several injured in a stampede at a soccer stadium in southern Guinea after clashes with fans. The stampede happened on Sunday the 1st of December and authorities are conducting an investigation to establish those who are responsible. And that's the latest from Jambo Newsroom. I'm Andrew Biney.
Need security? Call Alpha One Plus Limited, a strategic security resourcing platform that connects you with licensed security personnel. We cater for our clients' security needs, from manned guarding, door supervision, event security, all the way up to close personal protection. Alpha One Plus Limited, your one-stop security solution. Call now at 44-074-2526-7909 or send us an email on info@alphaoneplus.com.
Are you or a loved one living with high blood pressure, chronic kidney disease or asthma and looking for new treatment options? Clinical trials could be your next step. At Synexus Research Scotland, we are working to help advance medical research, and you can be part of it. Join a clinical trial that is assessing new treatments and providing expert care, and with the possibility of reimbursement for your time. Your safety is always our priority and participation is voluntary. To see if you qualify, call 0141 945 6850. That's 0141 945 6850 and quote the word radio. Come and get involved in research and help shape the future of medicine in your community.
Meet Sophie and Craig, stepping up to tackle climate change by car sharing to work.
Also, we're doing it to keep costs down.
Half the fuel means half the cash.
A dynamic duo if ever I saw one.
Can you see a parking space?
Together, they're helping to drive down Scotland's transport emissions.
Plus, Sophie's got great chat.
Sure. Do it for yourself and our planet. Search Let's Do Net Zero to learn more.
Established in 2006 as one of Glasgow's original mobile massage therapists, we deliver high-quality treatments with the ambition to forge permanent relations with clientele. We specialise in on-site massage, a type of treatment that has been specifically designed to complement the convenience and availability of massage at work. It is performed with the use of a specialist mobile chair, without the use of oils or the need to remove clothing. At Massage & Glow, we believe that massage should be a part of your everyday lifestyle. Regular massage not only relieves stress and tension, but also stimulates blood circulation, can help with pain management, and promotes good mental health. A must for your busy schedule. Various holistic therapies available. Contact us now on 07530 905 152 for your mobile massage therapist.
Are you a star baker or know someone who is? Applications for the next series of the Great British Bake Off are open.
Oh, that's exciting.
Are you a whiz with a whisk and ready to rise to the challenge?
An expert leader or the family's favourite feeder?
Do you love experimenting with flavours and sharing bakes with all your neighbours? Well, if you're a passionate, talented home baker, we want to hear from you.
Head to www.applyforbakeoff.co.uk to apply now.
Who knows? Maybe you'll be baking in the famous white tent next.
This is the Science Show with Dr. Dada. It's just so nice, you cannot do without. This is the Science Show with Dr. Dada. It's just so nice, you cannot do without.
Well, hello, and welcome to another
fantastic episode of the Science Show with Dr. Dada, broadcasting right here from the city of Glasgow. Today, as usual, we're going to plunge into the happenings in the world of STEM, that is science, technology, engineering, and mathematics. And we're exploring topics from all over the world. We'll be featuring some news highlights. We're going to be cracking science jokes, hopefully. And we're going to be answering the question of the week, or the topic of the week, which is what they're not telling you about quantum technologies. Perhaps you're asking yourself, well, that's a good question. What are they not telling me? Or perhaps you're asking yourself, who are they? Stay tuned. You're going to have the answers to all those questions on today's show. But if we explore that a little bit further, what if everything you thought you knew about the future of technology is missing one crucial piece, right? I'm sure you'd like to know what that is, right? So today we're going to uncover the untold story and, to hint at the unsung heroes behind quantum technologies and the game-changing potentials that they provide. Anyway, my name is Dr. Adetunmise Dada, and this is the Science Show on Jambo Radio Scotland. And we'd like to take this opportunity to shout out to our sponsors. IOP Scotland has been amazing, has supported this show. Today we have a sponsored show as well. We have Hamamatsu UK Limited sponsoring today's show. So we'd like to shout out to Hamamatsu for that. And we'd also like to say thank you to the Impact Acceleration Account, EPSRC, through the University of Glasgow. And we'd like to thank you, our listeners. Without you, we wouldn't be here in the first place. So let's introduce our guest, the special guest we have in the studio today. Today's guest, Jessica Steele, works with some of the most exciting developments in quantum technologies. And as you've known from following the show, and perhaps you've heard in other places as well, quantum technology is a field that's poised to revolutionize the way we do things, from communication to computing to sensing and so on. And as a UK representative for Hamamatsu's quantum applications, Jessica deals with advanced, and when I say advanced, I mean really advanced photonics technologies that enable groundbreaking research, including controlling light at a fundamental level and also involved in some form of detecting light as well. So exploring various degrees of freedom of light, like orbital angular momentum, states of light, and so on, even other spatial modes of light too. So her work is helping to unlock these amazing potentials of quantum states of light. And I would like Jessica to say hello to our listeners and our audience. It's really, really nice to have you with us in the studio, Jessica.
Thank you for having me. It's really great to be here.
Yeah, and you've made a long journey here as well, haven't you?
Yeah, about 7 hours drive yesterday.
Yeah, fantastic.
It was worth it.
Yes. I mean, for us, it really was really nice to have you here. And we'll hear a lot more about that as we progress with the show. So what we're going to do now is we're going to go into our first highlight for today's show. And it's one of the news headlines that caught my attention, and it's to do with what's inside the moon. I've seen all kinds of theories about what's inside the moon. Everything from, it's made of cheese. Perhaps you've heard that before. Like, there was a time when people said, maybe jokingly, that the moon is maybe made of cheese. Or there are some who also thought maybe the moon is actually hollow. Maybe it's something that's an installation where people have built it and there's a hollow empty space in it with maybe some aliens or whatever inside it. Well, it's confirmed, it's official. Scientists have confirmed what's inside the moon. So actually, among scientists, the debates have not been whether it's made of cheese or not. It's more been like, is it molten or is it solid, and what's the density of the core and all these kinds of things. But thanks to some incredible new research, we're finally going to get closer to a definitive answer. So what's fascinating about this research is that it combines data from different sources. So we're talking about different space missions, to, lunar laser ranging, to advanced modeling techniques to help paint a much clearer picture of what's inside, what's in the interior of the moon. And now we have a much clearer picture than we've ever had before. So it's a bit like having multiple detectives on the same case, and you piece all these, pieces of information together, and you get all the evidence that you need that points to this amazing new conclusion that the moon, wait for it, has a solid inner core. Wow. Da, da, da. It's solid. I mean, one would have thought, a lot of people would have thought, the moon has a molten core, right? Like a molten inner core. But it turns out that it's solid. It has the density similar to that of iron. So imagine it could be iron, who knows? But perhaps you're saying to yourself, well, you can't just dig. How do you actually know what's in there if you've not dug into it and, really looked into what you find? Well, scientists have different methods to study what's beneath the surface of a planet, of a planetary body like the moon, or a satellite like the moon. So it includes things like looking at how, the moon wobbles in its orbit, to studying some seismic data from some of the Apollo missions, to, listening to the moon, the vibrations of the moon, finding out what's going inside from doing that. So to use that analogy, it's a bit like listening to the heartbeat of a person, and based on that, working out what's going on with the heart. It's a little bit like that when it comes to finding out what the composition of the core of the moon is. So what they've heard, so to speak, is pretty remarkable. They found out that not only does the moon has a solid inner core, but also it has a fluid outer core. So it's solid in the middle, but, fluid, in the outer core of the moon. So that's interesting because it's not just all molten. You've got, because the pressure is that much intense in the inner core that it's so hot and so dense, it just becomes like a solid, like the density becomes like that of a solid. And that's really incredible, isn't it? But yeah, you can read more about that story, including the fact that the radius of that inner core is about 240 kilometers, and the outer core, extends to about 360 kilometers, and so on. So you can read more about that in the publication. It's published in Nature. Yeah, so that's about the best place you can publish that. It's a very, very impressive work, and it was published quite recently. First time it was published was last year. So the title of this story is "The Lunar Solid Inner Core and the Mantle Overturn." So you'll learn a lot from reading that paper. I encourage you to have a look. Good. So now that brings us back to Jessica. Once again, it's really nice. Thanks very much for joining us in the studio today. So what we're going to do now is we'd like you to take us, we'd like to get to know you. So we'd like to start from the beginning. So would you like to tell us where you grew up and where you were born? Let's start from that.
Okay, perfect. So I was born in a town called Pontefract in West Yorkshire,
I see.
which, fun fact, is where Haribo sweets are made.
Oh, Haribo sweets.
It's a good place to live. It smells like sweets for a lot of the year.
Good.
Really
That's nice.
So yeah, I was raised in Pontefract. So I've got both my parents and two siblings all raised together. So I'm a northern girl.
Nice.
You can't tell by the accent anymore.
I see. So what accent do you have now? I'm not the best at UK accents, apparently.
So mostly southern. There's the occasional northern word in there, but I mostly sound southern English.
I see. Nice. Very nice.
It's okay.
So yeah, Pontefract. I didn't know that name before.
No?
Yeah, Pontefract. It's like, what planet is that?
Yeah, it's quite a small town. Most people haven't heard of it. It's near Leeds. That's what people usually say.
Yeah, well, if you're listening to this show, well, you've heard it now anyway, right? So how would you say your childhood environment influenced your interest in science?
Ooh, so my mum is a mathematician and my dad studied chemistry and became an oil chemist. So we were very much a sit at the dining table and talk about science kind of family. And then, so my sister she studied pharmacology, and my brother is also a physicist.
Ooh,
so it definitely
nice.
runs in the family.
Yes, it does.
A lot of the environment growing up was very like scientific discussion, analysing things, sitting in the back garden and wobbling the washing line to show the harmonics of waves.
Ooh.
I remember that very clearly. My brother taught me about harmonics of waves in the back garden.
That's nice. I like that. I really like that. It's good. Do you get the discussions between, mathematicians and physicists about which one is more important and which one is better?
It's an ongoing argument in the family, everybody brings it up at least once at Christmas.
Yeah. I know a lot of the time some physicists likes to say, mathematics is just a language in which you express physics. Meanwhile, mathematicians are like, well, it's a little bit more than that. It helps you understand it, the universe. And there's this back and forth between the two groups of people, scientists, if you like. Yeah. Anyway, so as you look back, were there any moments during your school days, school years, that maybe sparked your curiosity about physics in particular?
Ooh.
Was there any teacher? You know how sometimes people have stories about a particular teacher that really helped them, or something else maybe?
I had some quite kind of cool teachers. I remember in college in particular we did a lot of kind of physical practicals, so we would all pretend to be an electron and run around the lab having different levels of energy and interacting.
That's brilliant.
Becoming a photon. So I think that helped push me towards it. Just general interest. I think I've been quite lucky to have a lot of quite inspirational people in my life, particularly from the science point of view. And the schools I went to definitely pushed STEM.
I see.
Yeah, just in general. So I feel quite lucky.
I see. I think I'm going to borrow that idea. That idea of running around pretending to be a photon or an electron or whatever.
You build an electrical circuit of people.
I see. That's really cool. Was that in secondary school or
I
primary
think it
school?
was so I went to secondary school and then a sixth form college that was separate. So it was the first year of sixth form college.
Oh, that's really cool. I'm going to borrow that. I don't want to say steal. I'm going to borrow it.
I want to see a video.
Yeah, that's really cool. So what about your, after secondary school, what was it about studying condensed matter at Warwick that captivated you particularly?
So Warwick kind of drew me in because it's a campus university. It's a really nice environment.
I see.
And I was just generally interested in their research. They also do a lot of work in astrophysics, so there's a lot of astrophysics courses that I was interested in.
I see.
As I reached kind of third year, I knew my strongest areas were related to condensed matter. So looking through the projects that were available, I spotted one on indium bismide, which was kind of, I think, it was theorized to be a really interesting material as a topological insulator. And it was working with Professor Gavin Bell, who is a really interesting guy. And as a bonus, he names a lot of the systems that he works on after characters from Doctor Who.
So that's nice.
I bonded with this group on a nerd level as well. It was very nice.
Oh, shout out to him, man. I hope he's listening. That's great. So indium bismide. And yeah. Can you tell us a little bit more about your experience working in that project? Was it an MSc project already, or was it just undergrad level?
So it was an integrated master's.
I see.
You could choose after 2 years whether to do a
Just
BSc
one more
and
year. Okay.
separate MSc, or to do a 4 years MPhys.
Okay.
So I went straight into the masters with no kind of separation.
I see.
But it was a really interesting project to work on. So we used molecular beam epitaxy.
I see.
In a massive vacuum chamber. So you're firing hot gases of indium and bismuth onto, we used a indium antimonide, I believe, substrate, just to see what happened, change the parameters, see if we could create indium bismuth, this lovely elusive material. Unfortunately, we only ever grew more bismuth. But we found out how not to make it indium
exactly.
bismuth.
That's the thing with science, isn't it?
Yeah, part of it is ruling out what not to do.
Yes, indeed. That's really nice. Yeah, that sounds like a really exciting project. And that sort of sparked your interest in continuing on in that sort of career path. So you've done, if I remember correctly, internal sales, and now you're representing Hamamatsu's quantum applications in the UK. That's quite impressive, isn't it?
I'm very excited.
So what inspired your move into quantum technology then?
So part of it was, so as an internal sales engineer, you at Hamamatsu, you work with a lot of academics.
Yeah.
We have a lot of application specialists, so anything that doesn't fit into the pre-existing application categories tends to be what the internal engineers work on most.
Okay.
And it just so happened that quantum, as an emerging kind of subject with a lot of new research, a lot of new contacts, was on the rise, and it just so happened that I got the opportunity to work on a lot of those projects.
That's cool.
Which was really exciting, and that just sparked my interest, and I didn't want to stop.
That's fantastic. Do you find yourself needing to learn more and more quantum as you go?
Absolutely. Every day there's a new kind of
new phenomenon or effect that you didn't know about before.
Yeah.
You're like, oh, okay. You'd learned about entanglement.
Yeah.
And of course, it starts with like single photon detection, right?
Yeah.
Detecting at the single photon level. And then you go into, actually, you can do communications. Oh, how does that work?
Yeah. How do you
superposition,
encrypt information?
Yeah.
How do you transfer it in the best way? What wavelengths are the best to use? Yeah. It goes on forever.
Yes, it does. It really does. That's not even an understatement, or overstatement rather. So outside of your work in quantum photonics now, you have some pretty interesting hobbies. Could you share some of them with us?
So a couple of years ago, I started learning how to crochet, and now I like to say I'm getting pretty good. I made a sparkly purple dragon for my partner's mum that I'm very proud of.
Nice.
And I've done a few bits of clothing as well.
I see.
So yeah, it's a hobby I really enjoy. It's very relaxing after a long day's work. You just sit with the wool and calm your mind.
I see. Very nice. And of course, we'll explore that a little bit more later. But there's a connection with Japan as well, with Hamamatsu. Yes. Has that moved you to learn Japanese at all?
I've started trying. So it's very different to English, and I've never learned a language properly before, so it's very hard to study. Props to anybody that can speak Japanese. But I've started. It's been a few months. I've got a couple of very basic sentences.
Like konnichiwa and
konnichiwa, watashi wa Jess. My name's Jess.
Oh, that's good. I like Japanese. Some people, when they hear my name, they think, oh, it sounds Japanese. I've heard a couple of people say that.
Yeah.
I say, oh, my name is Tumishi. I'm like, Tumishi sounds a bit Japanese.
Yeah.
Anyway, that brings us to our first music break, and we're going to be listening to Black Hole Odyssey, and we'll be right back.
Hey, let's go. Let's go. swallow a massive star. Don't even know what I am. I swallow a neutron star. I'm a beast, I'm a monster. I swallow a massive star. I'm a beast, I'm a monster. Above a jet of gas, freezing cold on the inside, incredibly hot just outside. I'm gonna bend your mind, even your space and time. If you come any closer, you'll be spaghettified. Hit you like a bulldozer, bugger the bye. Don't even know what I am. I swallow a massive star. Don't even know what I am. I swallow a neutron star. I'm a beast, I'm a monster. I swallow a massive star. I'm a beast, I'm a monster. Above a jet of gas. I'm attractive, I'm active. Matter falls as a captive. Evil stars radioactive. Spinning fast, never passive. Past my mental horizon. It's an eternal prison where infinity lives in. Time itself is frozen. Singularity, that's me. Dimensionality, zero. And my color is Nero. For the galaxy, I'm a hero. Don't even know what I am. I swallow a massive star. Don't even know what I am. I swallow a neutron star. I'm a beast, I'm a monster. I swallow a massive star. I'm a beast, I'm a monster. Above a jet of gas.
Yeah, that was Black Hole Odyssey, talking about black holes. So from the point of view, from the POV of a black hole, I'm a beast, I'm a monster, I swallow a massive star, blah blah blah. Perhaps you recognize my voice in that. It's a bit tuned a bit down, but yeah, I really had a lot of fun doing that. So Black Hole Odyssey, and this is the Science Show with Dr Dada on Jambo Radio Scotland, broadcasting live from the city of Glasgow. If you're just joining us, you're welcome. We've been talking about the thing that you're not being told about quantum technologies, or rather we're going to talk about that more in depth. And here with us, we're talking to Jess, who's from Hamamatsu Photonics UK, and we're going to talk to Jess a little bit more. But first, we're going to go into the second news highlight that we have today. And I grabbed this one from New Scientist. It says, tiniest ruler ever measures distances as small as an atom's width. That's, wow, that's mind-boggling. Imagine a ruler so small that you can measure the width of an atom with it. That's where we are. It's amazing. It's a breakthrough in measurement technology. And it's so precise. That's so precise. So scientists at Max Planck Institute for Multidisciplinary Sciences in Germany have created the smallest ruler ever. Now, this incredible feat is achieved using a technique that they called mean flux. And what it really does is it uses glowing molecules, laser light, and highly advanced microscope in combination to do these very, very precise measurements. It's a bit like when you shine laser light at a wall. Now imagine shrinking that laser beam down to the size of an atom. That's essentially what this new technology does. And the glowing molecules come into the picture because they are attached to different points on a larger molecule. So say, for example, a protein. And then the laser beam shaped like a donut. We're going to talk about shaping light very much in the next bit when we talk to Jess. But this laser beam is shaped like a donut, and then it homes in on the glow from these molecules. And based on the light that's emitted in the process, the scientists can pinpoint exactly what the distance between the glowing molecules are. So if you like, the molecules are like the markers of your ruler. It's like the ends of your ruler. And then using the laser, you interact with the material, and then you get a signature that tells you exactly what the distance between the two molecules are. That's absolutely mind-boggling, isn't it? It's like a mini GPS system. It's a bit like triangulation, if you're familiar with that. So you can pinpoint exactly what the dimensions are. You could ask yourself, well, why is this important? How does this affect me? Well, understanding the distance between atoms, especially within larger molecules like proteins, is quite crucial, from anything to do with, drug discovery to, looking into disease like Alzheimer's. So for example, Alzheimer's is a disease that is as a result of proteins folding incorrectly. And so by being able to measure these tiny distances, scientists can better understand how the folding happens, how proteins function, and perhaps even how to prevent them from folding in the wrong way. So this is something that's quite important. So these researchers, they've successfully, as we mentioned earlier, measured distances as small as 0.1 nanometers. That's about the size, the width of a typical atom. And they were even able to differentiate between the two forms of the same protein based solely on the distance between some specific points. So this is really groundbreaking stuff. And it's not a surprise that it's published in Science. The other one we talked about was published in Nature, right? This is published in Science, another one of the biggest sort of scientific journals that exist today. So the title of the paper, Direct Optical Measurement of Intramolecular Distances with Angstrom Precision. So angstrom is 0.1 nanometers. So that's really mind-boggling, isn't it? The first author's last name is Sal. So you could say Sal et al. Or, whatever they say. So this was published just in October 2024. And I really encourage you to have a look at this. This is really, really impressive research. Very good. So now let's get back to Jessica. So do you prefer to be called Jessica or Jess?
I'll answer to both, but usually people call me Jess.
People call you Jess. So we'll call you Jess. So Jess is going to tell us a little bit about more about her work at Hamamatsu. Yes. So, so perhaps we could start with Hamamatsu's global history and historical and global presence. So, could you tell us a bit about the origins of Hamamatsu in Japan and how the company has grown into the worldwide leader that it is? Just one or two things.
Yeah, of course. So the company originated back in 1953. We're based in Hamamatsu City in Japan. Mm-hmm. So originally it was Hamamatsu Television Company, just a few people in a lab.
Yeah.
And now we're up to 5,795 people, I believe. So we have 10 massive factories still in Hamamatsu City, as well as offices around the globe to offer local sales support and servicing.
Yeah.
In the 1980s, we changed name to Hamamatsu Photonics, mm-hmm. and in 1988, I believe, the UK office opened.
Wow.
So we've been open for 36 years, if my maths is right.
That's fantastic. And yeah, for those watching live and maybe the recorded version, you'll see, for context, the map there showing Hamamatsu in Japan. So that's really nice to see. So the map of Hamamatsu's global offices highlights its extensive reach, doesn't it? You can see it's a really multinational company. So how does this global presence impact the company's ability to support, quantum technologies in this case, and the innovation that's needed to push these ahead?
It's definitely beneficial. It means we can reach more groups who are doing more cutting edge research, so we can get involved. We can hear what they need, what we need to do to support them to make groundbreaking discoveries.
Yeah.
What is the next best thing? Well, maybe we don't know, maybe somebody else knows, and through just having a chat, getting in touch with us, we can get there together.
Yeah.
So it's really exciting to be able to work with so many different people and so many different backgrounds, and particularly for quantum, the expertise is spread out everywhere, and it can be so niche. So it's really nice to have the opportunity to get in touch with those people and collaborate together to make new things using our resources and their wonderful ideas.
Yeah, it's nice, isn't it? It's like a feedback loop, isn't it?
Yeah.
The research enables innovation, and the innovation enables more research, and it just keeps going like that, doesn't it?
Absolutely, yeah.
Yeah, there was this old video of Hamamatsu showing off some of their early technologies when it comes to single photon counting and doing like Young's double slit interference. I don't know if you've seen that video. It's a really nice one. I like to use that video a lot with my students. It's quite nice to see. So could we see the for those watching, could we see the map with the global offices, just to give us a picture of, you know, the presence of Hamamatsu? Yeah, so that's the one there, isn't it? So many locations all over the world. So yeah, it's really, really nice to see. So, but Hamamatsu's presence in Japan, particularly near iconic landmarks like in Mount Fuji, is quite intriguing, isn't it? So does this cultural or geographical context influence the company's work and values in any way, would you say? Just out of curiosity?
Yeah, I would say so. So I think everyone would agree that Japan is well known for its technology forward-mindedness.
Yes, absolutely.
And very reliable technologies, very kind of a lot of integrity. So we're very proud that I think nearly all of our products are manufactured in Hamamatsu City with that kind of Japanese quality, Japanese values. A lot of our products are assembled by hand still.
Wow.
Just because you cannot automate to the same level of quality.
Yeah.
We will do it by hand until we can find a better way.
Until we find some AI, maybe. Robots. But that's really nice to know. Like, it's done, handcrafted, if you like. That's really good. So let's talk a little bit more about some of the products then. So detectors are one thing. Hamamatsu has pretty much always been big on detectors. So how are these innovation, like detection technologies, how are they accelerating the timeline for advancements in quantum technologies, would you say that? Perhaps we could see the picture on the quantum technology applications, and yeah, that one. Yeah, Quantum 2.0 timeline, if you like.
Yeah, it's a lovely catchy headline that our American colleagues came up with.
Yeah.
I'm not 100% sure what it means, but I like the sound of it, so I'm going to use it.
Yeah.
So I think the detectors are integral to a lot of advancements in quantum. Without the hardware, you cannot do the experiments to prove the concepts. You can't make those advances. So particularly with things like single photon avalanche diodes for single photon detection, as well as things like our QCMOS camera, the Orca Quest, now the Orca Quest 2, which can do single photon resolution imaging up to 25 frames per second.
Wow.
Something like that previously may not have been dreamed of, but now it's really useful for research involving really low light, especially for quantum, for example, in kind of trapped ion quantum computing, for example.
Very nice. So that's is that the Orca Quest we're looking at?
Yes, that's right.
Fantastic. It really looks like a work of art, doesn't it?
Yeah, we're very proud of it. It's our flagship camera.
Fantastic. Yeah, I'm always fascinated by cameras that are, sensitive to the point of, single photon, because then you can do a lot with it. You can measure not just, the spatial location at the single photon level, but you can also do many interesting things. I know you have a product that does single photon resolving detection. Does the Orca do that?
Yes. So this can do single photon resolution in every single pixel. So there's 8
That's
megapixels
amazing.
in that camera, and if you were to say turn the lights off in this room and take a picture of you, you could then go into the camera
and see how many photons.
See how many photons are in each pixel, and you'd be able to see you in the picture even with all the lights off. It's amazing.
That's pretty impressive. I need one of those. I do need one of those. It's just nice because that means you have so much control. You can being able to resolve the number of photons. So how much is the resolution? So sometimes you have single photon resolution, but as the number of photons increases, the ability to discriminate between n and n plus 1 photons maybe reduces. So is it I'm guessing maybe a few on the order of like a few photons you can discriminate quite well, but then maybe more than a few.
I think off the top of my head, it's in the order of hundreds.
Okay.
But don't quote me on that.
Yeah, that would seem to make sense. I would imagine somewhere, above 100 photons, it becomes more and more difficult to tell.
Yeah.
But the applications are few photon in the few photon regime. So that's very nice. So there's also the photomultiplier tubes. Would you like to tell us about those? Can you tell us about some of the applications and use cases?
Yeah, absolutely. So our photomultiplier tubes, they're one of our kind of original products. We've been making these for many, many years.
From television days, I'm
from
guessing.
way back.
Yeah.
And we still hold a 90% market share globally for PMTs.
Wow.
They can be used for a massive range of different applications. So things like 2-photon microscopy, for examining the state of a qubit in a kind of a quantum computer, readout of a nitrogen vacancy sensor, a quantum sensor. You can use, we make very, very rugged versions of these that you can use for things like oil well logging, deep underground. It really is, sky's the limit. Anything you can think of where you need to detect a really low level of light, they have very high gain, so you can put in a very small signal of light, very small amount of light, and it will give you a very large electric signal, and you'll know the light is there.
Wow, that's very, very interesting. Very, very nice. I know some colleagues who use PMTs for like the few photon, single photon measurements, but I've not used PMTs before. I've used SPADs and SNSPDs, superconducting nanowire detectors, but PMTs are going to be quite neat technologies as well. Very, very, very interesting. And the SIPM component image, can we have a look at that? Can you tell us about that? So what are some specific use cases for these?
So these have a similar kind of use case to the photomultiplier tubes.
Yep.
They're for very low light detection. It's made up of an array of avalanche photodiodes.
Oh, I see.
So you've got loads of pixels feeding out into one channel, so it can detect one photon at once.
I see.
They are a little bit higher noise than photomultiplier tubes, but they are lower cost.
Okay.
So the two products kind of fill both sides of the market.
Very nice. I see. So is it like an array as well?
So you
have
like
a SPAD array type thing?
Kind of. So you can have you have your array of pixels that read out as one.
Okay.
And you can tile them together into large arrays. So for example, I believe there's a telescope.
Okay.
I want to say Subaru telescope, but I could be wrong. That uses a large array of tiled SIPMs.
Okay.
So if you want to cover a large area, these can do it because you can just keep tiling them. The only problem is the electronics at the back. You've got to have space for those.
Yeah. Okay. I see. So each unit acts as one.
Yeah. Each channel reads out as one, but it's full of thousands of pixels.
I see. Wow, that's really cool. Wow, we could spend all day talking about these devices, isn't it? I think the one I associate the most, just because of my experience with Hamamatsu, is the LCOS SLM.
Yes.
Maybe we'll talk about that after the music break. But for now, let's take another music break, and we're going to listen to another song. It's instrumental. It's entitled Vibe Control. We're talking about controlling light, and so now we're going to control the vibe for a couple of minutes. We'll be right back. Very good. That was Vibe Control. And this is the Science Show with Dr. Dada on Jambo Radio Scotland, broadcasting from Glasgow. And we are live. So just a reminder, you can catch us live on DAB. That's if you're in the car. So digital radio, you can listen to us. You can also listen and watch us live on YouTube. Also, you can listen to us live on jamboradio.co.uk. You can also listen through our app. There's a dedicated app on the app stores that's called Jambo Radio Scotland, and you can listen to us there as well. And you can also go to our YouTube channel and watch past episodes. And if you give us a follow and subscribe to our channel, that will be great as well. And we'd also like to take this moment to shout out once again to our sponsors. Obviously, today, Hamamatsu is in the house. So that's great. Shout out to Hamamatsu. We've got IOP Scotland as well as the EPSRC through the Impact Acceleration account at the University of Glasgow. So these are our supporters. We'd like to thank you, our listeners, as well, for tuning in and for staying on this dial. So now we're going to discuss the question for the week, or the topic of the week, which is what they're not telling you about quantum technology. We've been kind of hinting at it throughout, but now we're really going to spell it out, right? So quantum technology is something that's a bit like magic to a lot of people. You're talking about quantum computing, quantum communication, quantum sensing, and all these, fancy things that are going to revolutionize things and so on. But perhaps, by way of discussion, Jess, maybe we could throw this open. What would you say is one thing about quantum technology that would probably surprise or shock people? And there's no wrong answer here. Everybody would have maybe a slightly different take on it. But what would you say would be, I bet you didn't know that about quantum technology?
I'd say it's not necessarily a specific thing, but I'd say it's how much it is everywhere.
Yes.
Even if you don't think about it, there might be a little bit of quantum technology or quantum technology related science just in your everyday life. You never know. And hidden inside that, maybe there's a Hamamatsu detector. You never know.
Exactly. And that reminds me, I wanted to say something about the quantum 2.0. Yes. So people maybe mean different things when they say that, but one of the things they may mean is the fact that there was a quantum 1.0, which talks about things like the photoelectric effect. We all benefit from that. So the early sort of discoveries in quantum mechanics led to the creation of lasers, to the creation of photodiodes, and LEDs and these kinds of things. All these things that are in our phones, in our laptops, in all the devices around us. So now quantum 2.0 might be referring to the fact that now we're going a step further. We're going into quantum communications, entanglement and its applications, quantum computing and the rest of it. So like Jess said, there's quantum in most things in one form or the other, maybe quantum 1.0, so that's it. So that's something that might surprise people. Quantum is not as new as you think it is. You're using it, maybe depending on it every day of life. Another thing that might be surprising to a lot of people is how fragile quantum things can be, especially the quantum 2.0 kind of things, like entanglement, and when you're dealing with things like single atoms, single photons, the states can be so fragile. So you need the best of the best equipment to control them, to detect them reliably, and so on. And that's where Hamamatsu comes in, isn't it? So Hamamatsu's tools, things like the LCOS SLM and others, cameras and so on. Many researchers, including myself, during my PhD, a huge part of it was measuring high-dimensional entanglement through, using Hamamatsu SLMs, and that was absolutely amazing. It was really nice. So, what makes these tools indispensable when it comes to, these kinds of research? And is there a feature that or capability that maybe people maybe overlook? Maybe people don't get to hear about much?
So I think so people might not know something like, so the LCOS SLM, they're very popular for kind of 1064 nanometers.
Yeah.
But we also do slightly more obscure wavelengths, like 2 micron, that people don't tend to use as much, but there's a lot of possibilities out there.
Yes, indeed.
And things like the cameras, we have a wide range of cameras, from your Orca Quest, which is super low noise, no gain, could replace an EMCCD camera, for example. But we also have kind of your lower cost, slightly more stripped back cameras, which can also be really useful for quantum research. And can have a lot of interesting applications where you don't need the same sensitivity.
Exactly. Yeah. It's amazing, the capabilities of these these devices. And what's interesting is that a lot of the time, I review a lot of papers, and a lot of the time, you wonder what equipment the researchers used, right? You're like, okay, they did this nice work. What did they use? They just say, we detected it on the camera. Like, which camera, Sometimes it's important information as well. Like, in the spirit of science, you want to describe your findings in a way that it could be reproduced, right? And part of that is about mentioning, sometimes it's nice to mention, we use the Hamamatsu camera, right? We use this type of crystal, we use this type of detector. So I think in our paper, we did mention, that we used the Hamamatsu SLM. I think I remember, because I, had a hand in writing that paper. Can we see the cover of the Nature Physics? So back then, it was a long time ago now, so there it is. So you see that pattern. So the Hamamatsu SLMs helped shape, mold the intensity of the light and its phase as well. We don't show that there, but its phase as well. Really talking to all the 11, 12, 14 dimensions of the state of quantum light, which is quite nice. Anyway, so we often hear about the glamour of quantum breakthroughs, but behind the scenes, what you don't get told about is, we just bought this. Sometimes it's just a matter of, we bought this amazing device and it allowed us to do this new measurement. And sometimes that's the case. That's what happens, isn't it? So, talking about Nobel Prizes, I know for sure in 2022 there was the Nobel Prize in physics awarded to the researchers who discovered or who did pioneering experiments in quantum entanglement. So one of them was Anton Zeilinger. I know Anton Zeilinger uses a lot of his experiments involve the spatial degree of freedom, so orbital angular momentum, and I don't know for sure that he uses Hamamatsu SLMs, but that just tells us that these devices, they empower really, really groundbreaking stuff. So do you have any couple of other experiences to share in that regard as well?
Yeah, of course. So there's kind of 3 key Nobel Prizes that I'm aware of. There could be more that Hamamatsu have kind of famously been involved with. So there's the Kamiokande project, which found evidence of neutrino mass. So the experiment was back in 1987, but the Nobel Prize was awarded in 2002. Then the kind of second generation of that experiment, the Super Kamiokande, we were also involved in with so this is using our 20-inch PMTs. They were custom made for the project. Wow. They're humongous. They're amazing things to look at. But the Super Kamiokande project found evidence of neutrinos having mass. So the first one was first observation of neutrinos. Second one was neutrino mass. So that was Nobel Prize awarded in 2015, I believe. I see. And the third award that I know of is at CERN for the Higgs boson. Wow. So I think we provided some detectors for that.
Yes. Yes, that is deserving of an applause, isn't it? Yes. Thank you very much for sharing that with us. We could go on and on, couldn't we? But time is short. We need to wrap up now. But before we go, let's leave one joke. I prepared one. I'll just share that one. If that's okay. Or do you have one that you would like to share?
I have one. I don't know if it's very good though.
Yeah, please go for it.
Okay.
Go for it.
So, why don't photons need large suitcases on holiday?
Yes.
Because
Why?
they're traveling light.
Yes, fantastic. I like that one. They're traveling light. So, photons are traveling light, literally, right? So we play on words there. I've got another one. Why did the scientists break up with the photon detector? That's an he says it was too sensitive to everything they said. Yes, I knew you'd get that one. Anyway, that brings us to the end of our show today on this episode of The Science Show with Dr. Dada. And it's been really nice. It's been a blast sharing with Jessica on the amazing technologies that power the breakthroughs, some of the breakthroughs that we see in quantum technologies. So it's really been nice to have you join us as well. And for science enthusiasts and for those curious about the vibrant activity here in Scotland and even worldwide, remember that this is the right place to be, here on The Science Show with Dr. Dada. And I'd like to say a big thank you to you and to the team here in Jambo Radio. So to play us out, we're going to call on Tana Musica to sing this song entitled Lovely. And until next time, I'll say stay curious.
Only you they give me a ginger. No man can put us asunder. God Almighty join us together. True love is such a wonder. So you make the stars align. Not just because you are fine, yeah, but you have the beautiful mind. You're just so lovely, lovely, lovely. I will be best and come be fine like it is. Everything just perfect as it is. Dimple in the cheek and a nice white teeth. In the mind you discreet. Crown of the head to the feet. Everything's sweet. And when you smile it's over. You make me thank Jehovah.